scientists have a really good picture of the very early universe, something we know and love as the Big Bang Theory. In this model, a long time ago, the universe was far smaller, far hotter, and far denser than it is today. In that early inferno, 13.8 billion years ago, all the elements that make us what we are were formed in the span of about a dozen minutes. Even earlier, this thinking goes, at some point our entire universe, all the stars, all the galaxies, all the everything, was the size of a peach and had a temperature of over a quadrillion degrees. Amazingly, this fantastical story holds up to all current observations astronomers have done. Everything from observing the leftover electromagnetic radiation from the young universe to measuring the abundance of the lightest elements, and found that they all line up with what the Big Bang predicts. As far as we can tell, well, this is an accurate portrait of our early universe, but as good as it is, we know that the Big Bang picture is not complete. There's a puzzle piece missing, and that piece is the earliest moments of the universe itself. What came before the Big Bang? It's the question that always comes up when thinking about the origin of the universe. Most scientists simply ignore the question as it seems to be too hard a nut to crack. But now, in a bold revelation, physicist and professor of particle physics Brian Cox declared that he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head. Well, we used to think that the universe emerged in that state, very hot and very dense, at the beginning of time, and we used to call that the Big Bang. But now we strongly suspect that the universe existed before that, and in that sense, it's possible to speak of a time before the Big Bang. Join us as we dig deep into how Brian Cox debunks the Big Bang with the creation story that came before the existence of the universe. The idea of the Big Bang first came about back in the 1920s and 1930s when we looked out at distant galaxies. We discovered something peculiar: the farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing towards one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding today, and if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things get farther apart as time goes on, it also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, shorter is more energetic. That means the universe cools as we age, and hence, things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today in all directions that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Robert Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backward in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart. A time where matter and antimatter pairs could spontaneously form as the universe is so energetic that pairs of particles, antiparticles, can spontaneously be created. A time where individual protons and neutrons break down into a quark-gluon plasma as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus, and finally, a time where the density and temperature rise to infinite values as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, this singularity, represents where the laws of physics break down and is understood to represent the origin of space and time. This was the ultimate idea of the Big Bang. Of course, everything except that last point has been confirmed to be true. We've created quark-gluon plasmas in the lab, we've created matter-antimatter pairs, we've done the calculations for which light elements should form and in what abundances during the early stages of the universe, made the measurements, and found that they match with the Big Bang's predictions. Coming forward even farther, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures like stars and galaxies form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner, except that in a few regards, 3 specific things you would expect from the Big Bang didn't happen. First, the universe doesn't have different temperatures in different directions, even though an area billions of light-years away in one direction never had time since the Big Bang to interact with or exchange information with an area billions of light-years in the opposite direction. Second, the universe doesn't have a measurable spatial curvature that's different from zero, even though a universe that's perfectly spatially flat requires a perfect balance between the initial expansion and the matter and radiation density. And last, the universe doesn't have any leftover ultra-high-energy relics from the earliest times, even though the temperatures that would create these relics should have existed if the universe were arbitrarily hot. Theorists thinking about these problems started thinking of alternatives to a singularity, to the Big Bang, and rather of what could recreate that hot, dense, expanding, cooling state while avoiding these problems. In December of 1979, Alan Guth hit upon a solution. Instead of an arbitrarily hot, dense state, the universe could have begun from a state where there was no matter, no radiation, no antimatter, no neutrinos, and no particles at all. All the energy present in the universe would rather be bound up in the fabric of space itself, a form of vacuum energy which causes the universe to expand at an exponential rate. In this cosmic state, quantum fluctuations would still exist, and so as space expanded, these fluctuations would get stretched across the universe, creating regions with slightly more or slightly less than average energy densities. And finally, when this phase of the universe, this period of inflation, came to an end, that energy would get converted into matter and radiation, creating the hot, dense state synonymous with the Big Bang. This was regarded as a compelling but speculative idea, but there was a way to test it. If we were able to measure the fluctuations in the Big Bang's leftover glow and they exhibited a particular pattern consistent with inflation's predictions, that would be a smoking gun for inflation. Furthermore, those fluctuations would have to be very small in magnitude, small enough that the universe could never have reached the temperatures necessary to create high-energy relics, and much smaller than the temperatures and densities where space and time would appear to emerge from a singularity. In the 1990s, 2000s, and then again in the 2010s, we measured those fluctuations in detail and found exactly that. The conclusion was inescapable. The hot Big Bang definitely happened, but it's not the beginning of the universe. At that time, there is a question that always comes up when thinking about the origin of the universe: what came before? What happened before the Big Bang? And if there was no before, what was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy: some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including young Albert Einstein, assumed the universe itself to be eternal and everlasting. But now, most scientists simply ignore the question, as it seems to be too hard a nut to crack. In fact, when astronomers talk about the Big Bang, they usually do not refer to the very beginning of the universe, but to the incredibly hot and compact state of the universe in the first couple of minutes of its existence. To some extent, this is because no one has a real clue about the true nature of time, let alone about the beginning of time. British physicist Julian Barbour, for one, has argued that time doesn't even exist except as an illusion in our minds. According to others, including Stephen Hawking, time came into existence together with the universe, rendering the whole concept of the word before meaningless. As such, asking what happened before the Big Bang would be like asking what lies north of the North Pole or what distance is shorter than zero. Then again, we simply don't know whether or not there was time before the Big Bang. But Professor Brian Cox said that he has a bold idea. Never one to shy away from the big questions, Brian Cox expressed that he's ready to take on the story of the origin of our universe. The physicist investigated the crucial question of our existence, aiming to discover how the universe came to be. He discussed how discoveries of other galaxies have helped us comprehend how we came to be, as well as the technologies utilized along the route. As he looked at the different cutting-edge space missions that have gotten us closer to the answer, in a world-shattering revelation, Brian Cox argued there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series Universe, where everything begins and ends, stating that before the launch point of the Big Bang, there was no matter at all that existed was spacetime and an ocean of energy, almost still but gently rippling. This place, as he said, should be imagined as a near-still ocean of energy filling the void. It would have had no structures, and the energy in the space would have caused it to stretch violently, something known in space as inflation, flipping the Bible creation story on its head. Professor Cox proceeded to explain the science creation story, and the crux of the story is an unimaginably violent expansion, which is known as inflation. In the beginning, there was an ocean of energy that drove a rapid expansion of space, known as inflation. There were ripples in the ocean. As inflation ended, the ocean of energy was converted into matter at the Big Bang, and the pattern of the ripples was imprinted into our universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang. The denser regions of gas collapsed to form the first stars and the first galaxies, and 9 billion years later, a new star formed in the Milky Way, the Sun. The star was joined by 8 planets, including Earth, and nearly 13.8 billion years after it all began, we emerged blinking into the light. Notably, Brian Cox is not the only one to make such an argument about the beginning of the universe. Remarkable theoretical physics research has revealed a possible window into the very early universe, showing that it may be just the latest iteration of a bang-bounce cycle that has been going on for at least once and possibly forever. According to the study, the physics that we use to understand the early universe, a wonderfully complicated mishmash of general relativity and high-energy particle physics, can take us only so far before breaking down as we try to push deeper and deeper into the first moments of our cosmos. The math gets harder and harder to solve all the way to the point where it just quits. The main sign that we have terrain yet to be explored is the presence of a singularity or a point of infinite density at the beginning of the Big Bang. Taken at face value, this tells us that at one point, the universe was crammed into an infinitely tiny, infinitely dense point. This is obviously absurd, and what it really tells us is that we need new physics to solve this problem. Our current toolkit just isn't good enough to save the day. We need some new physics, something that is capable of handling gravity and the other forces combined at ultra-high energies, and that's exactly what string theory claims to be. A model of physics that is capable of handling gravity and the other forces combined at ultra-high energies, which means that string theory claims it can explain the earliest moments of the universe. One of the earliest string theory notions is the ekpyrotic universe, which comes from the Greek word for conflagration or fire. In this scenario, what we know as the Big Bang was sparked by something else happening before it. The Big Bang was not a beginning but one part of a larger process. Extending the ekpyrotic concept has led to a theory, again motivated by string theory, called cyclic cosmology. Technically, the idea of the universe continually repeating itself is thousands of years old and predates physics, but string theory gave the idea firm mathematical grounding. The cyclic universe goes about exactly as you might imagine, continually bouncing between big bangs and big crunches, potentially for eternity back in time and for eternity into the future. As cool as this sounds, early versions of the cyclic model had difficulty matching observations, which is a major deal when you're trying to do science and not just telling stories around the campfire. The main hurdle was agreeing with our observations of the cosmic microwave background, the fossil light leftover from when the universe was only 380,000 years old. While we can't see directly past that wall of light, if you start theoretically tinkering with the physics of the infant cosmos, you affect that afterglow light pattern. And so it seemed that a cyclic universe was a neat but incorrect idea. But the ekpyrotic torch has been kept lit over the years, and a paper published in March 2020 has explored the wrinkles in the mathematics and uncovered some previously missed opportunities. The two physicists who authored the study, Robert Brandenberger and Zhu Wang, both of McGill University in Canada, found that in the moment of the bounce when our universe shrinks to an incredibly small point and returns to a Big Bang state, it's possible to line everything up to get the proper observationally tested result. In other words, the complicated and admittedly poorly understood physics of this critical epoch may indeed allow for a radically revised view of our time and place in the cosmos. But to fully test this model, we'll have to wait for a new generation of cosmology experiments. So let's wait to break out the ekpyrotic champagne, but note that it's just one of many hypotheses in which our universe is not